As another example of a function we might want to try to graph, let's sketch a rational function, a quotient of one polynomial divided by another one. So note here that our function is undefined when x is equal to 2. So we should write out our domain here is going to be minus infinity to 2, union 2 to infinity. Here's our first and second derivatives. I already computed them. Note that these are never going to equal 0. But also note that you might say, oh look, the first and second derivative is undefined when x is equal to 2, but we're already excluding 2 from the domain of our function. So we don't have any critical points, and we don't have any places where the second derivative is 0. So the only place that we have to take into account is 2, which just isn't in the domain of our function. And so if we set up a sign chart for f prime and f double prime, so we see if x is less than 2, if x is less than 2, our x minus 2 is negative, but we're squaring that so it becomes positive. Negative divided by positive gives us something negative. If we are doing something bigger than 2, x minus 2 is positive, squaring that is positive. Negative divided by negative gives us negative. So here's our sign chart for the first derivative. Now how about for the second derivative? X minus 2 cubed is going to be positive if x is bigger than 2, and negative if x is less than 2, because we're cubing it. Okay, so this will be useful information for us. We also want to think about the behavior as the function goes to plus and minus infinity. So the limit as x goes to infinity of 3x plus 2 over 2x minus 4. And so this is infinity over infinity. We can do this very quickly with L'Hopital. So 3/2 is our answer here. The limit as x goes to infinity, so now, minus infinity is what we care about. Again, we're going to have an infinity over infinity, or I guess minus infinity over minus infinity in a determinate form. So again, L'Hopital's rule works here, and so we get 3/2. And then finally, we should think about the behavior as we're going to 2, because our function is undefined at 2. So we're going to think about the limits from the right and the left. As we get close to 2 from the right, 2x minus 4, that's a small positive number. 3x plus 2 would be getting close to 8. So positive divided by something small and positive, we're going off to positive infinity. But as we go to 2 from the left, 2x minus 4 is going to be a small negative number. 3x plus 2 divided by something small and negative, we're going off to minus infinity. So now we have all the information we need to make a nice pretty chart. And so for our nice pretty chart, let's draw some axes. And so what do we know? Well, let's draw on our asymptotes. So we have horizontal asymptotes at 3/2. And we have a vertical asymptote at 2. Okay, so now let's bring back our sign chart. Here's our sign chart. When x is less than 2, f prime is positive, f double prime is negative. So, that is the wrong sign chart. here's the correct sign chart. My apologies, that's from a previous version of this with a mistake. F prime is negative and F double prime is negative. So we are looking like this, decreasing and concave down. And furthermore, as we go to approach 2 from the left, we're going to minus infinity. And so our function is going to look like this. As we go to 2 from the left, we approach minus infinity. As we approach minus infinity, we have an asymptote at 3/2 here. And we're making that nice and concave down. Now, as we're bigger than 2, we are decreasing but concave up. So that's going to look like this. And this checks out with our asymptotes here. That as x goes to 2 from the right, we go off to positive infinity. And as x goes off to infinity, we go to 3/2. So here's our sketch of this rational function. We can get lots of information about it. Let's finish off this video with a second pre-class problem. So I want you to sketch this graph, x over x squared minus 9. I want you to carry out a similar analysis of, so transition points, asymptotes, make a nice pretty graph of this function.